Good morning, champs. When gases are compressed, pressure, volume, and temperature change together. But depending on heat transfer and irreversibilities, the compression can behave very differently. That is why we use polytropic processes. Let's compare the important process types first. The first case is isothermal compression. Isothermal means constant temperature, so the temperature does not change. During compression, heat leaves the gas fast enough to keep the temperature constant. Because the gas stays cooler, this process requires less work. The second case is adiabatic compression. Adiabatic means no heat transfer, so heat does not enter or leave the system. But this is important. Adiabatic does not automatically mean isentropic. Even if there is no heat transfer, friction and other irreversibilities can still exist, so the entropy can still increase. Now we define isentropic compression. Isentropic means constant entropy. An isentropic process is both adiabatic and reversible, so there is no heat transfer and no irreversibility. For an ideal gas, an isentropic process follows P times V to the power kappa equals constant. Here, kappa is the ratio of Cp to Cv. Because no heat leaves the gas, the temperature rises strongly during compression. Now, real compressors are usually not perfectly isothermal and not perfectly isentropic. They are somewhere in between. That is where the polytropic process comes in. A polytropic process follows P times V to the power n equals constant. The exponent n tells us how the compression behaves. If n equals 1, then we get P times V equals constant. That is the isothermal case. If n equals kappa, then we get the isentropic case for an ideal gas. And if n lies between 1 and kappa, then part of the heat leaves the system, but not enough to keep temperature constant. So the temperature still rises, but not as strongly as in the isentropic case. This is why n is so useful. A smaller n means more heat leaves the system. The temperature rises smaller. Compression is easier, and less work is required. A larger n means less heat leaves the system. The temperature rises stronger. Compression is harder, and more work is required. Now let's connect this to work. The boundary work is the integral of pressure with respect to volume. For a polytropic process, pressure times volume to the power n is constant. So pressure can be written as a constant times volume to the power minus n. When we insert this into the work integral and integrate, we get the polytropic work equation. The work equals P2V2 minus P1V1 divided by 1 minus n. This lets us calculate compression or expansion work directly. Now let's do a tiny example. Air is compressed polytropically. The initial pressure is 1 bar. The initial volume is 0.10 cubic meters. The final pressure is 5 bar. The polytropic exponent is 1.3. We want the final volume. We start from P1 times V1 to the power n equals P2 times V2 to the power n. Now rearrange for V2. V2 equals V1 times P1 over P2 raised to the power 1 over n. Insert the values. V2 equals 0.10 times 1 over 5 raised to the power 1 over 1.3. This gives approximately 0.029 cubic meters. So the volume decreases strongly during compression, and because the process is polytropic, the temperature also increases. To summarize, isothermal means constant temperature, adiabatic means no heat transfer. Isentropic means constant entropy and requires reversible adiabatic behavior. Polytropic is the more general case. It describes many real compression and expansion processes, and the exponent n tells us how strongly the temperature rises during the process.